So, so, good afternoon, everyone. So, we will start our today's live interacting session within a few minutes. So, we will wait few more minutes. Let's see others are joining or not. So, okay, we will start our today's interacting session. So, this is our eighth live interacting session. So, previously we have discussed about this fundamental of fluid mechanics and all these things. Even in the last classes, we have discussed about this dimensional analysis where we have studied how we can develop a prototype and this model assignment. And I hope that the previous live interacting session will help you to solve the assignment that has been given in this course. So first let me introduce myself. So I am Niloy, a PhD scholar from IIT Bhubaneswar and I am UTA for this course, Fluid Mechanics. So this course instructor is Professor Subhashi Datta from IIT Guwahati. I hope that all of you follow his courses regularly. So before starting this interacting session, let me have a brief about this course and what you will get to know from this course. So why we are studying this fluid mechanics? Because it's an interdisciplinary course and you will find its application in civil engineering, mechanical, chemical and even interdisciplinary sciences. So if a student have to solve problem like this flight problem or any aerodynamic design he is planning to do or any type of dam design, so he needs to have a knowledge about this force, fluid, properties of fluid and all this, how it works and all these things. So based on this course has been framed, and in the last classes, that is on the week 7th, what we have studied is that we have studied about this dimensional homogeneity, and also we have analyzed about this similarity about two model and where which non-dimensional number we need to use. These are the things we have discussed. So, if some of you are interested for this exam, please follow this live interacting session or this notes that has been delivered by Professor Subhashi. So that will definitely help you to score good in the exam. And even this certification code is quite important in terms of your academics. So coming to this today's uh, lecture, what we will initially do is that we will study about this vast topic that is incompressible viscous flow in pipe. Okay, so and in this what we are mainly dealing with, we are dealing with laminar and turbulent flow, and further we will be dealing with the losses in pipe fitting and also in some non-circular arrangement and path pipe flow and what are the things that is happening and how the concept that we will study from this thing will help us to solve any numerical problem, that thing we will learn. Okay, So my pattern should be like that. I will give you a question and I will give you 1 or 2 minutes to solve this one. And after that, I will discuss the relevant concept along with the solution and how you have to solve this through this fundamental. Right. So why I am doing this thing? Because I am assuming that you have gone through this lecture in the week lecture, and that will help you to solve this one. Basically, it's a life interacting session on numerical. Still, I will discuss about this concept in brief. Okay, so I'm moving to this first question. Also, before moving to this first question, you have studied about this Bernoulli's equation in the previous classes, right? Also, this continuity equation you have studied. So, this fundamental concept is also essential for this week assessment. So you should remember basically these two equation. One is this Bernoulli's equation and another is the continuity equation. That will help you to solve majority of this question. Though there is a new thing added in this assessment, so that we will discuss. Okay. So this is the first question. So the first question is that the average velocity for a fully developed laminar flow is what? So these are the four options. So please try to solve. I am giving you 2 minutes for this one. After that, I will discuss about this concept. So try on your side. If you are not able to solve, no issue. I will definitely discuss it in detail and about this concept and what are these things. So no need to worry. Just try to solve this one. So as so you try to solve this one. Still, I am giving you some hint about this laminar. You know this fundamental of this laminar and turbulent flow, right? So, what basically is a laminar and turbulent flow is? So, if you talk about this laminar flow, so laminar flow means the flow in which the fluid moves smoothly. That means it is always in a not linear, in an orderly pattern. Say say this is a fluid, right? Okay. So if these are the layer, if all the layers are moving in a similar pattern, then this is known as laminar flow. And it's what is its important characteristics? Basically, it generally follows straight path or curved path. Like if it is curved, every layer should be curved. So similarity should be there in a corresponding layer. Okay. So this is top layer, this is the bottom layer. So in between layers should be the similar pattern as that of the top and the bottom. So also another thing you need to remember that the velocity profile should be parabolic. Velocity profile parabolic. What that means? Say this is a pipe, right? So if it's Velocity profile is parabolic means the velocity is maximum at the center, whereas it is minimum or zero at the wall. If it is no slip condition, then velocity at the wall is zero. So like if you are moving towards center, this velocity will increase. So that is the pattern. So its profile should be like this one. So that is the velocity profile. This one is the velocity profile. See, that means the velocity is maximum at the center, whereas it is minimum at the wall. So that's why the velocity profile is always parabolic in laminar flow, right? Also, the flow is steady; it doesn't change with time. Okay. So, and how you get to know whether it's a laminar flow or no? So that thing you can easily understand if you go through some YouTube or animation video. You will see that if a flow is there and you are not able to understand whether it is flowing or it is steady, or it is in rest. So in that scenario, you will say that it's a laminar. Like sometime you will see that a water is coming from a pipe, so you will not see any changes. It's like it's a solid and it is fixed there. So that is not the scenario. Actually it's a laminar flow and each and every layer have the same features. So that's why this thing is observing. So basically there is a number, that is a Reynolds number, which we have studied in the previous class. Okay. So this Reynolds number, if this Reynolds number is less than 2000, then we know that it's a laminar flow. Okay, and if I talk about this turbulent flow means if there is a flow, this is a tube. If the first layer move like that, this second layer like, third layer is like that, but there no such uniform pattern is there between this layer. Then certain types of flow is known as turbulent flow. Okay. So what is its basic characteristic? Its basic characteristic it is random and fluctuating. Say if at one point it is, say here, if I take this point, it is downward, whereas here it is upward. Similarly, it may be upward or its velocity is more or less. Anything can be happen. We do not have any realistic idea about this fluid. Next is the velocity distribution is quite flatter. Like say in that case it's a parabolic. Say it's a symmetry, I can say. But in case of turbulent, it is not that scenario. And also in the laminar it is steady, but here it is not steady, it is unsteady. Okay. So and how you will get to know whether it's a turbulent flow? In that case you have to calculate the Reynolds number, and if you found that it is more than 4000, then it is known as turbulent flow. So a question may arise that if the number is less than 200, it is laminar, right? Then, and if it is more than 4000, it is turbulent. Then what happens if the Reynolds number is in between 2000 to 4000, right? So in that case, this flow is known as transition flow or transition region. So in that region, the flow is neither laminar neither turbulent. It is an intermediate flow. That means in that regions it may happen that some of the layer is turbulent and some of the layer is laminar. So that is the features of this region. That is Reynolds number from 2000 to 4000. I think you got this concept, right? So anyone would like to answer this question? Anyone? Or should I go for this solution? Okay, I am going for the solution. Let's see. Someone has answered. It's Ratul. Ruby also A. Good. Okay. So let us solve this question to check whether it is correct or not. So this concept, how to solve this one? This concept is basically based on this fundamental of integration. So basically, for a fully developed laminar flow. So what is a fully developed laminar flow? Basically, if it is a fully developed laminar flow, that means say this is a pipe, right? The flow is going there. Here the Reynolds number value is less than 2000, say, but the this nature, that means this velocity profile is parabolic or this nature. So that nature is observed after the fluid is traveling certain distance. Okay, so how you got to know this, the if the fluid is fully developed? So you have to check its velocity profile. If you found out that it's a parabolic, then it is a fully developed flow. Okay, so that is the thing. So here, since it is a fully developed flow, the profile is parabolic. So generally, if you have to find the velocity at a certain point, say u, so its formula is u equal to v max 1 minus r square by r square. So what basically here is r, capital R and small r, and what is Vmax? So Vmax is the velocity at the center. So we know the velocity is maximum at the center and is least at the wall, right? So this is your Vmax, and as it's a tube, so its diameter is, if its diameter is capital D, so its radius is r, right? So r is the radius of the tube, and small r means the distance from the center at which you want to find the velocity. Say if you want to find the velocity at this blue line, okay. So first you need to calculate the distance from the center. Say it is r. So at this r distance you need to find the velocity. So that is the formula here. Vr is Vmax. So you need to remember this thing throughout this lecture. So u r equal to v max 1 minus r square. That is the thing, right? Any confusion up to this? Okay. So now your, if I talk about this maximum velocity. So you have studied, if I have to find out the q, what is q? That is volume flow rate. We know that volume flow rate is a into v, right? That means if it's a pipe, if you have to find out the volume flow rate, you need to know this area. The area is known to you, that is A, and V. V is the velocity. So which velocity you will take? So you will have to take the average velocity, right? So I can write V average is Q by A. area we know because the diameter is we have assumed the radius as r, so we can easily find out this area. So what we need? We need this q. How you will find out this q? So to find out this q, what you need to do? You need to integrate. Okay. So how you will integrate this thing? For this integration, say this is the region. Say this is the tube, right? Through is the flow is flowing. So we know that is A into V. So this velocity at region, say at r distance, we have to find. So in this r distance, I can write this velocity as ur, and the area at this distance I need to know. So what will be the area? Can you tell me what will be the area here? I don't know. Say I assume this area as dA. Okay. So this blue line correspond to this blue line. If I draw, this is r, also similarly this is also r distance. So if I generate a circle, what will be the radius? Is the radius will be smaller. So correspondingly I can write in place of ur, this is V max 1 minus r square by this one, and in place of a I can write pi r square, right? So this value of r, so what is the minimum value of r? That is a center, which is 0. What is the maximum value of r? Is capital R. So now can we integrate now? Yes, because Vmax is constant, it will come out, and integration of pi r square is 2 pi r dr. So 2 pi I have kept outside, and it is 1 minus r square by this one, right, into r dr. So now you can integrate easily. So why I am doing this thing? Actually, there is direct formula. So I am just showing you this thing because if certain types of question comes, you will able to solve this like this way. So that's why I am showing this thing. So now we know integration, so we can easily do integration here. So r dr 1 into r dr, that means I can write it in place of this one. I can write r square by 2 r dr, integration of r dr is r square by 2, and integration here 1 by r square is constant, and small r square into r means r cube dr, so that is r to the power 4 by 4, that is 0 to capital R. Okay, so if you put it here, you will easily find out this value. So I am putting this value, that is V max into 2 pi, this is r square by 2 minus r to the power 4 by r square, that means r square by 4. So that is basically r square by 4. So we will get 2 pi V max r square by 2. That is the value of q we are getting, right? So this thing we have already got, that is 2 pi V max r square by 2, and area I know that this is pi r square. So r square is cancelling out. Sorry, it is 4. So this 2 will be cancelled by 2 and this pi will be cancelled out. So what I get? I get V max by 2. So that's why this correct answer is option A. Do you get this concept? Yes, everyone has answered it correctly. But this fundamental concept you need to know. So another important thing in double integration term, you have studied about this double integration term in engineering first year in maths. So one thing I am just using this thing, I am showing you another formula which will help you to solve it quite easily. So basically the formula of Q, if you use this formula, is velocity at a point into r dr d theta. Why this thing came? Say this is a circle, right? So if you have to find out this area, so how will you find out this area? This is r I know, okay. So this small region is dr, this is straight line, and this angle is theta. So if I consider this as a triangle, so I know this thing, okay. So I have to find out this, just a minute, I have made, sorry, this is dr, not this is dr, this is dl. So this is dr. So I can write dl means, you know, dr into sin theta. You have studied about this second, where this arc means L into R or L into sorry L into theta. So I can R into theta. So here I can write dr, and this is small, so I can write d theta. Is it? So this region is dr d theta, and since it is at a distance r from a certain region, that's why this r is here. So that fundamental formula you remember. If you remember this thing, most of the question you will easily able to solve this. And in this scenario, you just forgot about this image. So how you will solve? You know this value, and double integration is there, right? So first is it integration with respect to r and integration with respect to theta. So r, this r means this radius of this pipe. So its minimum value is 0 and its maximum value is r. And this theta, theta means this angle. So see, this is a full circle, so its minimum value should be 0 and its maximum value will be 2 pi. So one thing you can do, that you can first easily integrate with respect to d theta. Other terms are constant, so integration of d theta is theta. So this 2 pi will come out, and accordingly you can do integration. So that formula you try to remember. This is based on this double integration term that you have already studied. Okay. So now I am moving to this next question. So it's a theoretical question. So please try to answer. I am giving you 1 minute. So Ravi is saying viscosity. No, D, surface roughness. Ratul also option D. Just Kartikeya, please try. Okay. Yes, the correct option of is surface roughness. So just I am briefing a little about this thing. So what basically is Reynolds number is? Reynolds number basically is a ratio of inertial force by viscous force. From there you have understand this formula rho v L by mu. Sometimes you will find D. So that is another thing. Here what is rho? Rho is the density, v is the velocity, L is the characteristic length. So that characteristic length can be equal to diameter in case of a tube and based on the problem. And mu is the dynamic viscosity. Another thing in some of formula you know this kinematic viscosity. So what it is exactly? So it basically is dynamic viscosity by rho. Please remember this thing. In many of the cases that thing is given, so students are not able to answer this case at that moment. So if this is given, that means from the denominator you have to divide it by mu. Similarly from there you have to divide by rho, sorry. If you divide both the denominator and numerator by rho, you will get nu. So that is the formula. That means this will be divided by nu. So that types of question also come. I am not only explaining about this question, I am also explaining about this fundamental, and certain types of question can be asked in the exam. And in this formula, say this density is not related to surface tension, right? It's a fluid property. Velocity is also not related to surface tension, and L is a characteristic length. So it is not, it is diameter basic, or it may be diameter. So it is not a property on which the surface roughness depend. So in overall all other parameters, fluid viscosity is there, fluid velocity is there, fluid density is there, characteristic length is there, only this surface roughness is not there. So that's why the correct option is option D. Yes, everyone are correct in this one. So similar types of question, the next one. So please try to solve this one. Okay, here it is said that a fully developed flow is a circular pipe. So it is talking about a circular pipe. So here you have to tell this friction factor, that is F. So I hope that you know what is the friction factor. So I am just giving you 1 minute, and after that I will solve this one for you. So Ravi said option C. Raji, so let's see. Ratul, option B. So in this question, both of you have a contrasting point of view. Let's see who is correct in this respect. Okay, I am solving this one for you. So say for this, I think that you have studied about this Darcy friction factor, right? So what is a Darcy friction factor? Darcy friction factor. So basically, it's a formula which relates this friction factor with Reynolds number, which is 64 by Reynolds number. So that is a formula given by this Darcy. So it is known as Darcy friction factor. So it is basically for a fully developed laminar flow in a circular pipe. Always remember, for a fully developed flow, this is only applicable, not for not for other flow like this transient or turbulent flow. Okay, so this is only for fully developed laminar flow, not laminar flow. It should be fully developed laminar flow. So also some people say that it is not Darcy, it is Darcy which base, Darcy OH base equation. Okay, so in this expression, you see that it depends directly on this Reynolds number and no other terms is there. So I can directly say that this friction factor is a function of Reynolds number. And another important thing, apart from this question, as you know that it's a fully developed laminar flow, so it should be what it should be is velocity profile. It should be parabolic velocity profile. So as it is a parabolic velocity profile, that means there should be a balance of shear at the wall, right? So, so in that case, it always assume viscous flow, where surface tension doesn't change. Okay. So what I want to tell you is that uh, as we have said that these types of flow assumes in this formula they have assumed that it's a viscous flow. So this surface roughness here doesn't changes the linear viscous momentum distribution. That means the change in the velocity has no certain effect because of this viscosity. And always remember this roughness effect are always we are in 99% cases we consider this roughness effect negligible for this laminar flow. But in turbulent cases, we are not considered this surface roughness negligible. So, if in this question it say in a turbulent flow, the friction factor is a function of what? At that case, Ravi, your answer will be correct. That is both A and B should be the answer if it's a turbulent flow. But as it's a laminar flow, so it should be option B. Okay. So I am moving to this next question. So it's another theoretical question. So in this question, what it is, huh, in fluid flow analysis, which boundary condition can be expressed as the velocity of the fluid and the velocity of the wall are same. So please try to answer this in 1 minute, and after this I will discuss about this concept. So free surface again two contrasting answer. So let's see if anyone is answering or not. Okay, I am answering this one for you. See, but in this answer, no one of you are correct. So why I am to you? What basically this thing tells? So this is basically a no sleep condition. So what is a no sleep condition? No sleep boundary condition or no sleep condition. What it state? Say it is a plate. So fluid are moving in between this plate. So if the velocity of the plate is sorry, if the plate is at rest, so if plate is not moving, then in at that cases we have to assume the velocity near the wall, that is almost adjacent to the wall, should be zero. And if the say in another scenario, if the plate is moving, these two plate, this top one and this bottom one, if these two plates are moving at a velocity say 1 meter per second, so at that scenario I have to consider that the fluid near the wall, that should be also 1 meter per second. So that is the boundary condition. So this no slip boundary condition means a condition, and it's mainly for this viscous fluid that is in contact with the with the wall. Okay, so here this velocity should be same as velocity of the fluid adjacent to the boundary, should be same as that of the boundary. So for a stationary wall, what I said, this velocity at the wall is zero, so we can say this velocity of the fluid is also zero near the wall. So that is a basic assumption, and we have to take this assumption for any simulation based work. But in real life, the scenario is not there. There is a difference, relative velocity between the wall velocity and the liquid velocity near the wall, right? Say, so say in real life, the velocity near the wall, say 1 meter per second. Then, if the wall is also moving, then it should be a little more, like this way. So if I talk about this other option, so the correct answer is option B, no sleep condition. And why the other option are not the correct answer? So if I talk about this first option, that is the interface, means it is the layer between two fluid. So it doesn't guarantee whether both the fluid have same velocity. It may happen that one first fluid is of this velocity, next fluid is of another velocity. Next is the free surface. What is free surface? Free surface means interface. They say interface. If you talk about this interface, that means between two fluid. It may be liquid, liquid, liquid oil, liquid water, anything. But if someone say free surface, it will definitely between an interface between liquid and air. So that is a fundamental. And also symmetry. Symmetry means experimental condition. Say I talk about a scenario. Say this is a pipe, right? And this is a liquid domain. Say you are providing velocity, equal velocity throughout this region line, right? So this what so if in simulation if I have to do this thing, what I do, I just separate this one into two parts. So that's a symmetry boundary condition. That means whatever with the velocity, whatever with the proper. So see, whatever with the say the fluid is flowing like that over here. So at that case, similarly, the same phenomena will be reflected here. So that is a symmetry boundary condition. So if a body, if you feel that the system is like that, whatever way with the phenomena on the left side, it should be same as the right side. Then you can also report. So that is the thing. So the correct option is option B, no slip, where this velocity of the wall and the velocity of the fluid should be same at least. So I'm moving to this next question. This is another theoretical question where it is said that friction factor in a fully developed turbulent pipe flow depends on. Previous one was a laminar flow, but this one is for the turbulent flow. So do not get confused. Please try to answer this one. I am giving you 1 minute time. So I have already discussed this thing in the previous question, in the previous to previous question. Ravi, option A. Ratul, option E. Both are partially correct, but no one is fully correct. Why? Because see, as I have talked about this laminar flow and that too a fully developed laminar flow. What I have said that here at that case this friction factor depends on what? This Reynolds number, right? But I said that at this case it doesn't depends on this surface roughness. But here in this case, so what will happen? It's a turbulent flow. So turbulent flow is itself a disturbance is there. So why the disturbance is created in a flow? Say a pipe is there. If a flow is flowing through it, so disturbance will generate in its path. So that is basically the roughness of the tube is also can be a reason. So that's why turbulent layer is generated, turbulent flow is generated. So surface roughness should be the thing, but that is not the direct surface roughness. It is basically relative roughness. So why it is a relative roughness and not direct surface roughness? Surface roughness means say this is a surface, any surface, tabletop surface. So this look like that way. If you are focusing on a line, if I draw a line, this if you are focusing on this line, you will see it's almost straight line. But in microscope, if you follow this line, it will be like this types of line. So that types of nature you will see, right? So that is basically a roughness. So in case of turbulent flow, if this is the tube, okay, if this is a tube, so there should be this is roughness. But if you increase the size of the tube, the roughness should be same. So at that case, you will not be able to distinguish which one is the which case, right? So that's why this roughness, say roughness, if I represent this roughness as small r, this roughness by d is a parameter which is used in this friction factor. Okay, so that's why the correct option is Reynolds number and relative roughness. So why relative roughness is used? Because if you increase the diameter of the U, then at that cases roughness will not directly play a vital role. There are certain parameter, and that parameter is the is surface roughness. So the correct option is Reynolds number and relative velocity, which is option B, D. So option D is the correct option. So this is your correct answer. So I am moving to this next question. So and also giving you 2 minute time. Please try to solve this one. So Rabi, option A. So previous answer you understand, Ratul and Ravi. I hope so. So this is the situation where this pitot probe or pitot tube is used for what? So already Ravi has answered. So the same answer again, same answer. Yes, option A is the correct answer. So you know it's fundamental. That is, you know that pitot tube is used for flow speed measurement. That is right. But can you know this fundamental on what fundamental principle it is working? So the fundamental principle is that basically a pitot tube measure pressure. Okay. So a pitot tube generally measure pressure between 2 points. One is the stagnation pressure and another is a static pressure. So the difference between the two pressure, what is a stagnation pressure and static? Okay. So that two pressure is basically measure, and the difference between these two pressure is known as dynamic pressure. So what basically this thing indicate? So so that means basically it indicates the pressure difference between a point which is at rest and the pressure difference between a point which is moving. So the difference of these 2 points is known as dynamic pressure. So say if I represent P T minus PS, or say PT is the stagnation pressure or the total pressure. Okay. So the difference of these two, one is known as del P, which is our dynamic pressure. Is this okay? So now you see I am applying Bernoulli's equation. So why I am applying Bernoulli's equation? Say at 2 points, say point 1 and point 2. So I am not telling any details right now about this point. If I apply Bernoulli's equation, what I will get? P, sorry, this is T point and this is S. T is corresponding to stagnation and S is corresponding to static. So I can write V square by, this one is not there, 2G, here is a rho there, plus ZT is PS by rho, right, plus Vs square by 2G plus ZS. Say we consider that both these two positions are at the same point. So I can cancel out this thing, right? So can I write? So if I take PS at a side, PT by PS is rho equal to Vs square by 2G minus Vt square by 2G. So here rho G is there. Sorry, here G is not there. So that is the thing. So you know that this value is 0 because it is at rest. So I can get this thing Pt minus Ps, that is del P. Del P I will get, rho will goes to here, is 1 by 2 rho V square, is it? So from there you can find out this velocity. So that is the principle that is used here. So it is used for the measurement of flow speed measurement. Okay. So that is the concept. So as it is giving, in some question it may be given that whether it will only give velocity. Say if a device is giving you velocity, that means it is also giving you volumetric flow rate, because we know that Q is equal to A into V. Area of the tube we know, and velocity you can find out from this tube. So indirectly it is helping us to find Q, right? So certain question can also be asked. Is it clear to everyone? So see how Bernoulli's equation helps us to get this equation. So that is basically this fundamental, nothing else. So I'm moving to this next question. So here uh, the concept is the ratio of the momentum correction factor to this energy correction factor for a laminar flow in a pipe is what? So I think this concept maybe you haven't studied till now. Okay. Just I am giving you the formula. So momentum correction factor means uh, in kinetic energy correction term, those two correction terms are there basically. So why we are using this correction term? Say Bernoulli's equation has certain limitation or certain assumption that it should be steady, should be non-viscous like that, and all these things. So, but in real life, no fluid should be uh, no fluid should be idle. So there is certain things, certain changes in property or certain default defects there. So to consider these defects, what we need to do, say this in the Bernoulli's equation, the terms like P by rho plus V square by 2 plus Z. So that types of terms are there. So if you talking about this term, this is the pressure term, this is the kinetic term, this is your uh, datum term or your potential term. So these each and every term are not this each say this pressure term. This pressure term is only for ideal cases. If this is not an ideal case, if some changes in fluid property or viscosity is there, that certain things should be multiplied with this term so that we will get the exact thing. Similarly for these velocity terms and all these things. Okay. So based on this, you have to find out this question. Oh, sorry, there is G is there. Just forgot to write G. So please try, or can I give you this formula? Also in the previous one, sorry, I just there is G and there is G also. I just forgot to write, or you can write G here. So that G will be cancel out. So that's why I haven't cancelled it accordingly. So this kinetic so for this kinetic term, there is a correction coefficient. So momentum correction coefficient is generally represented by beta and this energy correction is represented by alpha. Generally, this energy correction term is for this one, this term. So what is the formula? This formula is basically, please remember this formula because that will help you to alpha, that is for energy. So for energy, the correction formula is double integration. So U of R, you remember R dr d theta you study. So just in that formula, there is a cube there. Okay. And that thing should be into this. And what is it? It should be divided by Q. So here, this should be average velocity into area, because this term represent area, so it should be area, corresponding area, and this is q. So that is for alpha, and for beta, beta is for the momentum. So in case of momentum, the same equation is there, only it is a square. by V average Q square into pi R square. So that is the formula. So using these two formula, find alpha and beta initially. You know you are, or I need to write it for you. Okay, I am writing this for you. You are basically is V, or I can write as V max into 1 minus R square by small r square. And what is V average? V average we got in the first question, it is V max by 2. So now you can solve this one. Please try to solve this one. Just tell me what is the value of alpha you are getting and beta. Please write it in the chat box. So I am giving you 2 minute time to solve this integration. So similar types of question you can expect. Anyone? Please try to solve. So just tell me the value of alpha first. Ratu says that the alpha is 2. So what about beta? So Ravi, please try. Or will I show this for you? Also beta is saying that it is 4 by 3. Okay. One more minute I will wait and then I will go for the solution. Okay, I am showing you this solution. Just say I am just showing you the solution for beta and you will solve alpha. You will try to solve alpha. Okay. Say this beta. I say that double integration is there. So this is double integration. U means I know that V max or U max 1 minus R square by capital R square. This whole should be square into R dr d theta. This integration should be 0 to R and this should be 0 to 2 pi, right? And the below is V average into area, that is pi R square, right? The same, this is velocity into area, this is velocity, sorry, this is velocity square into area, above one is also same, but it is with respect to integration. So see, first it is with respect to theta. With respect to theta, there is no other theta term. So every other term should be constant. Only we have to integrate d theta, that is theta. So this 2 pi will come out, and this is square term. Square term matlab that V max will come out, and in integration it should be 0 to r. If V max come out, so I have to integrate this one 1 minus r to the power 4 by capital R to the power 4 plus minus 2 r square r to the power r square, this whole into r dr. So that will be the term. So now you can integrate. First one is integrating with respect to, sorry, in place of V max I can V average, I can write V max by 2, or V average V max I can write 2 into this one. So 2 pi into 4V average square R square by 2. One to R to the power 6. Next one is minus 2 by R square R cube R to the power 4 by 4, and this integration should be with respect to 0 to R. So you just do this thing. So that is 0 to R. That integration should be r to 0. So that is 2 pi, 8 pi v average square. So there should be here r square by 2 plus r square by 6 minus r square by 2. Any confusion up to this? Huh. So that 2 will cancel out. This one is the top divided by, so the denominator will remain same. V average into pi r square into V average into pi r square. Four by 3, which is 4 by 3. Similarly, you can find out alpha. Okay. If you solve alpha, alpha will be 2. So, Ratul, your answer is correct. So, you need to find out the ratio of beta by alpha, because beta is momentum equation I have considered beta by alpha. So, if you calculate beta by alpha, you will get, that is the solution. So, I think you understand this thing. So, in this way, you can solve this one. So, I hope that you will be able to solve this integration. So, now I am moving to this next question. It's a theoretical question. Please try to answer. So, I have received an answer. Okay, I am just giving answering this one for you. So basically, in this question, it is talked about this loss of energy at the exit of a submerged pipe is. So in that case, a submerged jet means a pipe. Say this is a pipe. Okay. So this pipe is submerged in a large reservoir. So this is a large reservoir. In that reservoir, it has been ejected. So what will happen? There is a kinetic energy at this region. So it is asked what will happen to its kinetic energy at the exit of this submerged. So yeah, while entering this pipe, I know this velocity head is v square by 2g, right? If I assume this Bernoulli's equation on all other conditions should be in accordance with Bernoulli's, right? So that should means v square by 2g will enter this block, and say this is a large, very large reservoir. So in that reservoir, what will happen? This kinetic energy get distributed. Okay. So yes or no? That means this kinetic energy that is associated with this flow is getting dissipated in the reservoir. So that is the scenario. So what is getting dissipated? The whole kinetic energy. So then what is the loss? The loss is the whole kinetic energy, that is v square by rho g. In real life, it is not exactly v square by 2g. It is a little bit less. Okay. So here say little bit, that means c, and this c term is generally 1. That's why we consider both this as same, nothing else. So the correct option is option B. Have you got my response? Have you understand this thing? Yes or no? So that is v square by 2g. So now I am moving to this next one. Here says the loss of energy at the entry of the submerged is. Here it's a, if it is the entry of the submerged, then what will happen? Again, I am giving you 2 minutes time. No 2 minutes, just 1 minute. Previous one was the exit of a submerged pipe. Now it is the entry of a submerged pipe. So in the entry of a submerged pipe, what basically is happening? See also I am okay. Ratul is answering option A. Okay, I'm checking. So what exactly is happening in this scenario? So the entrance in the given scenario, it is the at the entry point of the submerge. So at the entry point of the submerge means it should be from a larger reservoir should be there, and from which the liquid is coming out. So that is the basically this fundamental. So what will happen? So if this is the kinetic energy, whatever may be the kinetic energy that has been entered, because here is a sharp edge. Okay. So this equation should be, what should be the previous equation? V square by 2g. So this V square by 2g should be there. So this V square, so in order to, because large volume is there, so some volume is have to here. So in order to do this, a k constant should be added with this figure. And it has been observed that from a larger to the smaller one, this k should be equal to 0.5. So that is the correct option is option A. So that is the correct option. So now I am moving to the next one. So this is the hydraulic gradient represent what? So I have already discussed this point in the last class. So please try to answer this one. I am giving you 2 minutes. So Ratul has answered option C. Okay. So let us. So actually, this hydraulic gradient line, that thing has already been discussed in the previous class. So So generally, in if we talk about any pipe flow, there are basically two grade of piping. So these are hydraulic gradient line SGL, and another is total gradient line, or we also know it as energy gradient line. So these are the two gradient line you will get to know in any pipe flow. It is also known as grade. Okay, so what basically it is? It is basically this summation of datum head plus pressure head, or so see, if I talk about this Bernoulli's equation, what is there? There is pressure head plus kinetic head plus datum head. So three heads are there. So if I take this pressure and this datum head, then it is known as hydraulic hydraulic grade line, sorry, or yeah, hydraulic gradient line. And next is energy gradient line. Energy gradient line basically is the summation of all these head. That is pressure head plus velocity head is also known as kinetic head is also known as velocity head. So both this term can be used, plus another is datum head. So this datum head is also known as another name of datum elevation head. So both these terms should be both these things can be used. So what is the pressure rate? Pressure rate basically means P by rho g, and velocity head is v square by 2g, and datum line is z, datum head. So in case of AGL, what is not there? There is no velocity or kinetic term. Okay, this is also known as kinetic. So in this question, it is asked hydraulic gradient line represent the sum of what? It is the sum of pressure and datum head. So which will be the option? Pressure head and datum. Option C will be the correct option. Okay, so this is the answer. So I think someone has replied. Yes, it's the correct answer. So now I am moving to the next question. So it's a numerical question. So in this numerical question, it is basically based on this piping laws which I have discussed earlier. So please try to solve this one. Here it is said that a valve in a piping system causes 3.5-meter head loss, and if the velocity of the flow is 7 meter per second, the loss of coefficient of this valve is what? Basically what, as I have told, that if suppose in a, let us talk about a pipe, two pipe. Say first there is a bigger pipe and there is a small pipe. So what will happen in the bigger pipe, whatever will be the velocity head or this kinetic head generated, if it goes to the smaller pipe, and for a real life scenario like it is in viscous flow, so what will happen? So there is some losses. So that's why, that means this velocity head, what is the formula of this velocity head? This is v square by, generally this is v square by 2g. Okay, in this pipe, if after that if goes here, and for it is for real life scenario. In case of any other scenario, that thing is quite different. So say little change, not a significant change, is there little change in that case, this loss is given by k into, k means a constant, into this velocity here. This is also known as minor losses. So that thing you will see in verbs, in entrance, and all these things. So please try to solve this one. So this is corresponds to the head loss. So say I represent head loss as HL. So that is the formula. So please try to solve. So I am giving you 1 minute time. So basically this head loss, what this head loss represent? This represent how much energy is lost because of the change in shape or this bending. This is not the total head that is gone into this next pipe. It is basically the loss. Please try to solve this one. Here what is given? Here this head loss is given, that is HL is given, velocity is given. So you just have to find out this value of K, nothing else. Yes, Ratul said option D. Okay, so let us check. So first in such types of question, you first have to identify what is given. See, in this question, it is already given head loss is there. So no need to think of another thing. So whatever be the formula of head, so you should have to multiply a K or constant with it. Someone has, yes, option D. Yes, them. So two people have answered. So in this question, the head loss, that means HL is given as 3.5 and velocity is given as 7 meter per second. So just put this value here. This is 3.5 into K 7 square by 9.81 into 2. So that is the thing, it is given here. So you just have to find out this value of K. So if I 3.5 equal to K into, if I calculate this one, what I will get? V square by this one, 49 by around 19.5. That is, it is somehow near to 2 point. Just a minute, let me calculate. It's around 2.5, not exactly around. So K I will get around 1 point something, 3.5 by 2.4. is around 1.4. So the correct option is option D. Okay, so it's a simple question. Such types of question you can also expect. So now I am moving to an advanced question based on this concept. So also the similar types of question you, where losses are not there. So you have already solved in the previous life interacting session. So now in this question, what is given? In this question, it is given that the water flows in a pipe, where also the velocity is given. The head loss is given as 10, but that means HL is given. So you are asked to find out this pumping power uh, to overcome these head losses, and value of G is given. So it's a simple thing. So power loss, you know the formula of power loss. Just use this one and you will be able to solve. So I am giving you 1 more minute. And after that, see, I think that you have studied about this formula. You know this formula of power, how to find out this power in fluid. So just use this one. Just I am giving you a hint. Option A. Mr. Pritham has said it is option A. So for the others, I'm giving you an hint. That means in fluid, while studying this power concept, so power is basically a function of pressure and the flow rate. So you can use this concept also. Okay, I am solving this one for you all. So basically, as I have said, power, you know these two formula of power. One is okay, power is change in pressure into flow rate. So this was the previous formula where pressure means P del P here, change in pressure. That means rho G H into flow rate is Q. Q means A into V also you can use. Accordingly, this one is the formula which we have studied previously, right? So also another formula not another formula. You can see here what is H. H is the head. What head? It is the potential head. But here one head loss is there. So they haven't talked about what type of head loss. So in the current scenario, if I use this formula, so this power is rho g h, head loss is there. So that's why HL, replace H by HL into Q. Q means A into B. So that is basically the formula. Okay. So now what is given in this question? First, this diameter is given. Diameter is given as 15 centimeter, which is 0.15 meter. Next is velocity given as, always write down this thing in a question paper, in an answer sheet with respect to a question. So head loss is 10 meter, right? So I got this D I got, so I can find out A. A is pi d square by 4. So accordingly you just put the value and you will find out a certain value. So let me calculate this one. 3.1. So what I will get is 0.017 meter square. I got A, I got B, I got HL. It's a water, so rho I know. This is 1000, right? Also G I know it is 9.8. So just I need to put all these value, nothing else. 1000 into 9.8 or 9.81, whatever you want, into HL is 10, area is 0.017, and velocity is 1.8. So you just put all these value. So I will get 3120 around, what is equivalent approximate, which is 3.12 kilowatt. So yes, Mr. Pritham is correct. So that types of question you can also expect. So that is the thing. So it is a simple formula. Always remember this: power is pressure, change in pressure into flow rate. Also also you can find another formula, which is weight flow rate into head. So weight flow rate means rho g. Okay, that is weight flow rate. So flow rate means Q. Weight means rho g into flow rate Q. Rho g into Q is weight flow rate. Okay, and into head. Head means HL. Any type of head it would be. So if you put this thing, you will get P. Now I am moving to this next question. So we have two more questions for today. So it's a fundamental question where a pipe is having three branches, that is in parallel, and then initially it is a single pipe, and then it is branches into three pipe, and given that this three pipe is having same diameter and friction factor, and after that it also rejoin and again goes downstream. Now the thing is that this length of pipe 1 and length of pipe 2, I think that you, this picture is visible to you, right? So it is given, but the length of the pipe 3 is not given. Whereas this velocity of 2 and 3 is given, but 1 is not given. But ultimately we need to find out this length of the pipe 3. So that is our fundamental concept. So it is basically this. So I'm just giving you this, recalling this thing, this Dutch Weisbach formula or Mazur loss formula. What is it? It is HL, head loss is friction HL B square by 2GDT. This is the fundamental formula all of you know. F is a friction factor, right? And all these things you know. So now in this question, all the three pipe is having same diameter and friction factor is also same. So what I know, for parallel flow between say in any types of parallel flow, well, like this problem given here. So what is the main thing is that this friction factor, sorry, this head loss should be equal in each one. Like if I talk about pipe 1 and pipe 2, say this is pipe 1 and pipe 2 if I take. So in that case, the whatever be the H of L in pipe 1 and H of L in pipe 2, that should be equal. Just now I can write FLB square, correspondingly I can write GD F of 1, L of 1, B of 1, D of 1, F of 2, L of 2, B of 2. What is given here? Diameter of each and every one is D1, D2 and D3 are equal. Also F1, F2, F3 are same. So I can cancel out F1 and F2, right? This thing also cancel out and D1, D2 is also cancel out. So from here, what is given, length of pipe 1 and pipe 2 are given. So I can find out and velocity of pipe 2 is given but 1 is not given. So I can find out V1, right? So please find out V1. Because what is given in this question, L1 to 5 meter, L2 8 meter and V2 2 meter. So if you put down this thing, you will get a certain value. V1 is L2 by L1 root into V2 square. So I am getting this as this one. So I am getting V1 as 2.53. Now I got V1, right? Also I have V2, or even similarly in pipe 1 I have length 1 and length 3. So length 3 I need to find. So either you can show the similar thing for pipe 1 and pipe 3, or pipe 2 and pipe 3. You can get this value of L. Please, I am giving you 1 minute. So Ratul is saying option B. Yes, option B is the correct answer. Good. So calculating this for L3, we will get similarly the B will be the correct answer. So now for this last question for today, it is a similar types of question. So basically in this question two reservoirs are connected as given in the picture. So its length is given, diameter is given, gate valve is also given. The pipe entrance is sharp, so its head loss corresponding K value is given, and the valve is half open. Its also loss coefficient is given. So two coefficient is given, one at the entrance and another for the half open, and the head difference between the two reservoirs is given as 20. That means the total head loss is given. Okay. So assume the friction factor. So you are asked to find this thing. So I am just solving this one. It's a critical, not a critical one. Actually, it's a question based on the total head loss. So if I talk about this total head loss, say I represent the total head loss as H. What basically H is? H is this. You have Darcy friction factor, from where we have got this measure heat loss. This one is my measure loss, pipe loss. Plus we have few more loss. These are the minor. What is this is here, it is talking about the sharp entrance. That means say K entrance into something, entrance into B square by 2G. Also there is valve is half open, so that thing is also given. So for this valve there is some which is V square by 2G, and anything is given. See, and another loss is there, right? What is the loss? This one is the entrance, therefore should be exit, because it is the entrance. This is the valve, for this corresponding valve there, and there should be an entrance. For this entrance, we know that for the entrance it is say K. exit, sorry, not entrance, exit, v square by 2g. This is equivalent to 1, right? So I can write this h is fl by d plus ke plus kv plus k exit if I take v square by 2g outside. So in this question, what is given? This ke is my zero point 0.5 and kv is 5.5 given, right? This one. And k exit we have already know it's always we consider it as 1, as I have studied, as we have studied in question 6 or 7, right? Like that. So I can put this the value. F is friction factor is known or not? Friction factor, friction factor is 0.4. F is 0.04. L is 1000. D is zero point 0.4 and H is given, H is 20. If you put all these things, you will find out what is not known. V is not known. So you can find out the V from here, putting all these value, right? So you will get V is 1.93 like that. Okay. So as you got V, you can find out Q. Q is A into V. Area you know pi by 4 d square. Accordingly you can find and you will get the answer as 0.24, which is option B. So option B is the correct answer in this scenario. So what we did, we basically find out these major losses as shown in this. So this is our major loss plus minor loss. In the minor loss, what I have considered? I have considered the entrance loss plus the valve loss plus the exit loss. In the question, this entrance loss coefficient is given, valve loss coefficient is given, but the exit coefficient is not given. We consider in the exit it is the full head which is lost. So that's why K is 1. In other cases, it's a small like zero point 0.5 or like that. Uh, so in the always remember in the exit it is 1. So putting all this value as already H is given, I can find V. Now discharge I know that Q is A into V. Accordingly, I can find this one. So that's why option B is the correct answer. I think you up to this is for today. I think you understand this. Any confusion up to this? So I hope no such confusion. And if you have any confusion, you can mail me in my corresponding mail ID. And also, if you wish to follow the previous notes or classes, you can go through the link provided from this NPTEL site. And please follow this lecture given in the classes and this live interacting session numerical you just follow, which will help you to solve this assignment that is given in this given for these courses. So I hope that you enjoy this course and we will come up with the next live interacting session on the next Saturday. Up to this, bye and have a good day.